As you saw in the first video, radioactivity is a natural process that takes different amounts of time depending on which element you're talking about. Some elements decay very, very quickly into other elements. Some of them take millions and millions of years to go through that process. We're going to start by talking about nuclear reactions. When we talk about the structure of an atom, we know that the nucleus is small and dense. That means there's a lot of material packed into a very small amount of space. And it's roughly 2.4 times 10 to the 14th grams per centimeter cubed. And what that means is that if you had a marble, okay, and it had the same density as that of the nucleus of an atom, that marble would weigh about 250 million tons. So there is a lot of material packed into a very small amount of space. And it does not take up most of the space of the atom. Remember, most of the atom is empty space with the electrons zooming around outside of that nucleus. And inside of our nucleus, we have two different subatomic particles. We have our positive protons and our neutral neutrons. There are other particles that we have discovered in the Large Hadron Collider and at CERN, things like quarks and leptons and bosons, and they're going to be involved in kind of holding that nucleus together. Because whenever you think about the charges, again, we said protons are positive, but neutrons have zero charge. And we know that like charges repel, so you would think all of those positive protons would be pushing away from each other. There's got to be some sort of force that's holding them there. And sometimes that's called the strong force, sometimes it's called binding energy. And if you want to picture it, it's almost like you have all these protons and neutrons kind of moving around amongst each other, and then there are these rubber bands wrapped around them that they're able to move away a little bit. It's kind of like a bungee, but then it pulls it back in to the middle of that nucleus. But if there's not enough of that binding energy to hold them all together, then one of those bungees will snap and some of our particles can go flying, and we end up with a different atom than what we started with. We call it unstable whenever it's not able to maintain its configuration, and in order to become more stable, it's going to emit particles or waves of energy. And that process of emitting those particles or energy waves is known as radioactivity. Radiation. The particles and waves are known as radiation. Sorry about that. And there's been several different elements that are kind of more well known than others for being radioactive. Whenever Henri Becquerel was doing some experiments back in 1896, he discovered that one of our more popular elements, uranium, was quite radioactive. And you've probably heard of Marie and Pierre Curie. They discovered two other radioactive elements, polonium and radium, which you can tell by the name, it's going to be radioactive. Whenever high energy particles or waves are emitted from the unstable nucleus, that process is radioactivity. Whenever those particles are emitted, and it has to be particles here, things that have actual matter in them, okay, that will change the nucleus of the atom and it will turn into a different element than what you started with. And that's a process known as radioactive decay. It is decaying into a different element. It's also sometimes called transmutation. If you think about what it means to mutate, it means to change. So it's changing to a new element. And we get a formation of different atoms. If instead of having particles being emitted, we have waves of energy, okay, there's no actual matter, it's just energy coming off of it, that will not change the identity of the atom. It's only losing energy. It's still radiation and it's still potentially harmful or beneficial depending on how it's being used, but it will not change what the actual atom is. It just helps it become more stable because there's not so much energy moving around there. Now, earlier in the year, we learned about different forms of an atom, that they're all the same element, but they have different numbers of neutrons. And those are going to be called isotopes. Atoms of an element that have the same number of protons, they're the same element, but they have different numbers of neutrons. Some are heavier, some are lighter. And if you have a radioactive isotope or a radioisotope, those are going to be isotopes of an element that are unstable. There's not enough binding energy to hold it all together, and it will emit radiation. Could be either radioactive decay, losing particles, or waves of energy. And just to kind of review how we will write our symbols for our isotopes, we have our general format given here where X is going to be the element symbol from the periodic table. The bottom number here is going to be our atomic number, which is the same thing as the number of protons. And then the top number is our mass number, which remember is the mass of the nucleus, which means it's the protons and neutrons added together. The electrons weigh so little that they're not going to contribute to the overall mass that we're going to be concerned with. So what is the symbol for an isotope of cobalt that has 33 neutrons? So the first thing is just to figure out, well, what's the symbol for cobalt? So we go and we look at our periodic table. We find that cobalt is going to be number, let's see, 27, and its symbol is CO. So we'll go ahead and write our symbol. And since it is atomic number 27, that means there are 27 protons. That number will go on the bottom. And we're not writing a fraction. We're not going to draw a line. It's just one number on top of the other, like in our example. We need to add the protons and neutrons together. So we said our protons were 27. They tell us in the example that there are 33 neutrons. So to find that mass number that's going to go on top, we just add them together. So we end up with 60, and that number goes on top. And if we wanted to write a name for this instead of just having a symbol, remember you would just write the name of the element, a hyphen, and then whatever this top number is here, that number goes after the hyphen. So that's how you would write the name for that particular isotope of cobalt. Now, there are different types of radiation depending on what's being emitted from the nucleus of the atom. And the first type of radiation we're going to look at is the emission of alpha particles. Whenever we handwrite alpha, alpha is a Greek letter, it typically looks more like that, like a sideways fishy thing. And it is positively charged. And all it is just a helium nucleus. So whenever we look up helium on our periodic table, in the nucleus there's 2 protons because its atomic number is 2. And there are going to be 2 neutrons there with it. That's inside the nucleus. Since it's only the nucleus, it's not the whole atom, there are no electrons around it, and that's how come we end up with a positive charge for that. It has a low penetrating ability. That means that it cannot go through many things at all because in this atomic world, it's actually pretty chunky. It's kind of like an 18-wheeler trying to move through things. So paper will stop it. It can't go through your skin or anything like that. Whenever we write the symbol in a nuclear equation, we have 4 over 2, because remember the atomic number, 2 protons goes on the bottom, and then the 2 neutrons with it will make 4 for the mass number on top. And it's our very large elements above bismuth, which is number 83, that are going to go through this alpha decay, emitting these alpha particles. So an example we have here is starting with an isotope of californium. And if this is going to go through alpha decay, or alpha radiation, then we know we're going to be removing this particle. And this is just like in algebra, whatever's on one side has to add up to equal what you have on the other of our arrow here. So since our bottom number right here is a 98, then that means that the 2 bottom numbers on the right-hand side of our arrow also have to be 98. So if we're removing 2 protons from 98, we're going to be left with 96. And then the same thing with the top. If we have 251 right here, we take 4 of those particles away, and we're left with 247. 251 is equal to 247 plus 4, which is 251. The new isotope that we made, this curium atom here, is what we refer to as a daughter nuclide. Okay, it was produced, it was made. I don't know why it's not a son nuclide, but we call it a daughter nuclide. And you just have a little reminder there about how everything has to add up. So let's see if we can't do an example here. We're starting with an isotope of platinum. And we can see over here that it is going to be alpha decay. We're going to be losing that helium nucleus. So if we have 78, what number plus 2 is going to give us 78? That's going to be 76. 76 plus 2 is 78. And then we do the same thing with the top number. We have 190. What number plus 4 gets us 190? We're basically just doing 190 minus 4, and we're left with 186. That will be your mass number on top. Now, if we want to figure out what the identity of this daughter nuclide is, we have to look up one of those numbers on the periodic table, and we're going to be looking up the atomic number, the number of protons. That's the bottom number. If you tried to look up 186, it's not up there. The table doesn't go that far. So we're looking up number 76. So we find that kind of in the center of our table there, and that's going to be osmium with a symbol of OS. And so that will be the identity of that daughter nuclide. Alpha particles, really just a helium nucleus. Our symbol is 4/2He. Low penetrating ability, cannot go through very many things. Okay. There is a second type of decay where the nucleus is going to be changing. It's called beta decay. And whenever you handwrite the beta symbol, it's kind of like a curvy B. And this is going to be a negatively charged particle because it's basically just an electron. And what's happening essentially, and you saw in the video before, you're starting with a neutron in the nucleus and it's losing energy and breaking apart to leave a proton behind, and it's emitting that electron out. And it's going to have moderate penetrating ability. It can go through paper because it's a lot smaller, but things like wood will stop it. So it still can't go through all that many things. Our symbol that we're going to write for beta is going to be 0/-1e. We put the E for electron. We put a -1 on the bottom because it's not a proton. There are no protons there. And whenever we lose it, we're actually going to increase how many protons we have. So we're not going to say that we're taking away a proton. We have to put a -1 there to kind of show that we're actually going to be increasing that proton number. But we're not going to be changing the overall mass number because we're taking a neutron and essentially turning it into a proton whenever we release that electron. So the mass number, the overall number of particles in that nucleus, stays the same. If you have elements with too many neutrons to be stable, there's too many particles there all jumbling around with that binding energy trying to hold them there, then it's going to go through this process. Whenever you have a closer ratio between the neutrons and protons, then it's going to be more stable. So our example, we're starting with an isotope of manganese, Mn. It's got 25 protons, and the protons and neutrons together total 56. So if it's going to go through beta decay, then it's going to be taking 1 away from some number in order to get this 25 over here. So think about what number could you put here, where if you subtract 1, we get 25, and that's how we end up with a 26. And when you look up number 26 on your table, it's iron, Fe, and that's how we got our symbol. The top number, the mass number, doesn't change. Again, remember this is a 0, so what number plus 0 gets us 56? 56. So let's look at example 3. We're starting with an isotope of terbium, and we have a 65 for the number of protons. So you have to think what number, right here, minus 1 will leave us with 65. Okay? If you're tempted to put 64 and you wrote that, then think about it. If you do 64 minus 1, do you get 65? No. So think about the numbers, make sure it makes sense. If you have 66 minus 1, then we'll get 65. The top number, again, won't change. So 161 plus 0 gives us 161. Remember, we're going to look at the bottom number to find the identity of our daughter nuclide. So we look up number 66 on our table. That's going to be down in the rare earth elements. That's going to be dy or dysprosium. So you'll notice with alpha decay, we ended up with a smaller atom when you look at the number of protons. It kind of went back on the table. With beta decay, though, in order to become more stable, it's actually moving forward. It's becoming an element that's a little bit further in the table. The beta particles are smaller than alpha. They're negative because they're an electron, and they have more ability to go through things than alpha, but they still can't go through just anything. Okay, the last type of radiation we're going to look at today is not any type of decay. There's no particle involved. It's just going to be the release of energy, and we call that gamma radiation. Whenever it's typed, it looks kind of like a Y, but whenever you handwrite it, it's more like a nose-diving fish, okay? And it is chargeless. There's no charge. It's not positive. It's not negative. It's just a wave of energy, and it has very high penetrating ability, okay? Things like lead might stop it, but it can go through most things. And this is the one that's going to be harmful to your DNA, okay? It can cause mutations and things like that. But since we're not actually removing any matter from the nucleus, it does not change the identity of our atom. We are not changing the protons. We're not changing the neutrons. All we're doing is releasing energy. So our symbol for that is 0 over 0 because we're not changing any particles. And then we have our gamma symbol. So we're going to practice identifying what type of radiation we have, as well as determining the daughter nuclide that's produced or finding the particle that's being given off. So remember, each time we have an arrow, think of it like an equal sign for what we're doing. If we have 93, how do we get 93? What do we have to do to 94 in order to end up with 93? We have to do 94 minus 1. And whenever you look at your three different options that we talked about, we have alpha, we have beta, and we have gamma. So whenever you look at those three choices, the one that ends with a -1 on the bottom here is going to be our beta particle. And if you look at the top numbers, 239 is equal to 239 plus 0. So our type of radiation is going to be beta decay. On our next example, we start with uranium 238 has 92 protons. So 92 is equal to 92 plus 0. 238 is equal to 238 plus 0. So look at your options. We can see that it's going to be this last one, and that's going to be gamma, but do not put gamma decay. Decay indicates that we're changing it into a different element and that it's losing mass or matter, which in this case, all it's doing is giving off energy. So it's going to be gamma radiation. Alpha and beta are both decay, but gamma is radiation only. And a very clear way of knowing that you have copied someone's paper is if you have 0 over 0, but you write it as an 8. So do your own work. Okay, last one here. We've got an isotope of radon. It has 86 protons. So 86 is equal to 84 plus 2. And then we look at the top number. We have 220 is equal to 216 plus 4. So we look at our options. That's going to be He. A helium nucleus is an alpha particle. So this is going to be alpha decay. Not radiation, but decay, because it has decayed into a different element. Okay. On your assignment that you're going to look at today, on the front, you're just going to identify what type of radiation you have by what it is able to go through. And you have a little chart to remind you that alpha, beta, and gamma can or cannot go through these different materials. You have pictures over here, so you'll look at these and determine what type of radiation number 1 is. If it gets stopped by paper, is that going to be alpha, beta, or gamma? On the second one, if it can go through paper, but it gets stopped by wood, look at your chart and see which type it is. And then the same thing with number 3. On the bottom, you have a sample of radium inside of a lead box, and the opening allows 3 kinds of radiation to escape. Above the opening is a region of positive space, so you have a field with positive force up above. And on the bottom of the opening is a negatively charged region. And remember that opposite charges attract and like charges repel. And you have your 3 different types of radiation, alpha, beta, and gamma. Think about what charges those have. Think about if they would be pulled towards one side or the other, or would they be able to go straight through with no effect like we see here on number 2. So you'll just need to identify each one of these things is either alpha, beta, or gamma, depending on how it's being pulled. And you don't have to answer them over here. You will answer them in the 3 blanks that are provided. On the back of this assignment, you have some practice, just like we saw in the notes. You're going to identify either the daughter nuclide that's being formed or the particle that's being released. So you see you have some of both. If there's just 2 different elements given, like on number 3 here, that's exactly like we did in the notes. You have to figure out what the missing particle is there and then identify as either alpha, beta, or gamma on the right. If you have something like number 1, we notice that 4/2He is one of our 3 types of radiation that we're looking at. That's going to be alpha decay. And you do need to write decay if it's alpha or beta, radiation if it's gamma. But we have to figure out what that daughter nuclide is that's missing there, like the examples we did earlier on. So you've got 78 is equal to what number plus 2? So basically 78 minus 2 is going to give us 76. And if you think about it, 76 plus 2 gets us 78. And it's that bottom number we're going to look at to see what the element is. So we look up number 76. We saw that earlier in our notes already, and that's osmium. We still have to find out what the top number is, though. We have 190. So what number plus 4 gets 190? That's going to be 186. And you'll just continue with this, and you need to work on it for the rest of the class period. If you finish it, turn it in. And if you don't finish it before you leave today, it is due tomorrow.